So we're going to do another hypothesis test. We're still dealing with sigma is unknown. This was just a little bit different than what we had before. So a generic drugs are lower cost substitutes to brand name drugs. Before a generic drug can be sold in the United States, it must be tested and found to perform equivalently to the brand name product. So the U.S. Food and Drug Administration is now supervising the test of a new generic ointment. The brand name ointment is known to deliver a mean of 3.5 micrograms of active ingredient to each square centimeter of skin that's exposed to. As part of the testing, 7 subjects apply the ointment. 6 hours later, the amount of drug that has been absorbed in the skin is measured. The amount in micrograms are 2.6, 3.2, 2.1, 3, 3.1, 2.9, and 3.7. So how strong is the evidence that the mean amount absorbed differ from 3.5 micrograms? And we're going to use a significance level of 0.01, so 1%. So let's just kind of set up what we're looking at first. So what we have is a situation. We know that when we're comparing this to the brand name ointment, we should be getting a mean absorption of 3.5 micrograms of active ingredient. And what we're trying to show is that the alternate drug, we want to see if it's doing the same thing as it should be. So what we're hoping is that we are seeing an absorption of 3.5 micrograms, but like I said, we're seeing if it's going to give the same amount of absorption. So like I said here, so before the generic brands can be sold, it must be tested and found to perform equivalently to the name brand, which means that if it's not performing equivalently, my choice is simply it's not performing equivalent. So this is going to be a two-tailed test. So whatever T is, we're looking at two tails, and the p-value is going to be the combination of what we get out of those two tails. Remember, half a p is in one and half a p is in the other. The problem is that we do not have a sample mean and a sample standard deviation, but we have ways to find that. So all I did is I took the sample that we had, all those absorption rates, and I just put them into my first list. So one of the ways we can go about doing this is that we just simply go to stats and we calculate our one-var statistics on the sample and make sure that what we collect is the sample information. So from the sample, we know that we have a sample size of 7. We know that the mean of the sample is going to be 2.94. So we're doing a bunch of rounding here just to point that out. My S, because we need sample mean, that's going to be, or sample standard deviation, I'm sorry, would be this one right here. So that's 0. We'll just round it to 5 because that's the best I can round it to, I think. Yeah. So that's what we're seeing here. So what we're just trying to see is this so far removed that the sample is not performing the same as the brand name, or is it close enough that it's probably performing like the brand name? So I need to find my test statistic. So remember, this is X minus mu divided by S divided by the square root of N. So X is going to be 2.94 minus my mean, which is over here, 3.5, because that is what happens with the brand name, divided by a standard deviation of 0.5 divided by a square root of my sample size, which is 7. So let me clear this stuff off my screen here. So we'll just put it in here. So parentheses 2.49 minus 3.5, close parentheses, divided by, and I'm going to do parentheses again, 0.5 divided by second square root of 7. Well, that came out accurately close to what we had before. So my test statistic is negative 2.96. So what I originally needed was either I need to find a mean that is greater than, what was that, 2.94, or we were looking for a mean that is less than 2.94. And it looks like we're going to be looking at the less than because we got a negative z-score. So the p-value that my t-score would be less than negative 2.96. So we're looking really in this tail for right now. So that's one of the weird things about the two-tail test is you're really just picking one tail to look at eventually. And because my sample mean is less than what I have for my null hypothesis, we're going to look at this tail. And then because we're just seeing if it's different, we're going to end up doubling that score when we find it. So let's get out of here. We're going to go to second bars. Go to number 6. So T value, or the T table for a T table CDF is really what it is. And because we're looking at this smaller tail, the lower end of this is -1. So this is, like I said, we're going to infinity, but as close as we can get. So -1 followed by several zeros. We max out at -2.96. And my degrees of freedom, in this case, I had a sample size of 7, so I have 6 degrees of freedom. So I'm getting that probability is actually going to be 0.0126. We'll round to there. So my p-value is just going to be double that. So I'm going to do 2 times. So I'm going to do second. And right there, you see answer. Puts my answer in there so I can see what it looks like doubled. And I'm getting 0.025. So alpha was 0.01. So we have our p-value is greater than alpha. We fail to reject the null hypothesis. So what we have is we don't have evidence that it's not working the same as the name brand. So we do not have evidence the new ointment is not so we do not have evidence that the new ointment is not comparable to the brand name. So what we ended up saying is that it looks like it passed the test. We can market this now because it appears that even though it looks like it's a little lower with, like I said, with this, it's not so low that it's so far away from 3.5 on average to say that it's not working. So we don't have evidence that's not working. So that's all we can say. Because remember, what we're looking for is evidence to support the alternate hypothesis. We can't support the null hypothesis. So when we fail to reject the null hypothesis, all we can do is say we don't have evidence to the contrary. So we do not have evidence that the new ointment is not comparable, or the old ointment's new ointment is not comparable to the brand name. I said brand new, it's a brand name. The other way I can use the calculator once again is that t-test. So remember, I did enter my data in here because I needed that mean and standard deviation from the sample. So we could go to stat and we go over to test And we go down to number 2, a test. So last time we were looking at entering stats. This time we're going to enter in data because we put that data in there. So what we're going to do is down here, we want to make sure that my frequency list is L1. So once again, null hypothesis says the mean is 3.5. Our sample here is an L1. And we have to decide what kind of test we're going to do. And we had said that we were just doing a two-tail test. So we're going to look at the mean is not going to be the same as 3.5. So we calculate. So here it says mean is not 3.5. We got that same test statistic of negative 2.95. So we had 9.6 when we did it last time because there was rounding involved. Our p-value is still going to be 0.025 or 26. Like I said, it's just slightly off because we rounded the mean and the standard deviation when we did it, but we're seeing that same thing again. P is 0.026 in this case. Alpha was 0.01. So we're seeing that P is still greater than alpha. We fail to reject the null hypothesis, meaning we don't have evidence that the new ointment is not the same as the brand name ointment. All right, so run through this one more time. Figure out what we're doing. So Russell 2000 is a group of 2,000 small company stocks. On a recent day, a random sample of 35 of these stocks had a mean price of 26.89 with a standard deviation from the sample of 23.41. A stock market analyst predicted the mean price of all 2,000 stocks would be $25. So, can we conclude that the mean price differs from $25,000? So we're saying as an analyst before this happened, made a prediction, and they said it's going to be $25. The alternate hypothesis to this is that they were wrong, and we just want to know if it differs. So the alternate hypothesis is it's just simply not 25. Okay. So like I said, there are two ways that we can go about this. So we're looking at this kind of test, a two-tailed test again. So we're going to need some sort of test statistic here. We're centered at 25, so we either were in this tail or this tail. So what we're going to end up looking at is because my mean for my sample is 26.89, we're just going to do our analysis on this tail at first. So I just want to first figure out what is the probability that my X bar would be greater than 26.89. So that's essentially what we're looking for here. So we need a test statistic for that. So T is going to be my sample mean of 26.89 minus the mean from the hypothesis test of 25. My standard deviation for my sample is 23.41, and this is divided by the square root of my sample size, which was 35. So we're going to get T is going to be okay here, 26.89 minus 25 divided by 23.41 divided by the square root of 35. Be careful, you made a square root in there. Square root of 35, this is going to be 0.48. So just remember there is rounding involved here. So when I do this the other way, we're going to might get slightly different answers. So what I'm really looking for, what is the probability that T is greater than 0.48? Okay, so let's go to the TI-84. All right, so in this case, I already have my T-score, so I'm just going to go to second bars to my distributions. I go to number 6, and I'm looking at this area is what I'm bound. So it's bound between 26.8. Oops, sorry. It's bound between the t-scores now. So it is bound between 0.48. It's maxing out at infinity, so just extremely large number in there. And we had a sample size of 35, so we have 34 degrees of freedom. Okay. So I had to go back and check quickly. So our alpha level was a 5% alpha. And we see this p-value, the p-value actually going to be double that score, right? Because we're doing a two-tailed test. So my p-value is actually going to be double my 0.32. So we got a really high p here, but definitely what we're seeing is that p is greater than alpha. So we fail to reject the null hypothesis. And because we fail to reject the whole null hypothesis, we do not have evidence that the analyst was wrong. So the analysts predicted a combined mean of 25, and we got 26.89. What we're saying here is that that's not really that far off. We don't have evidence that that analyst was wrong about their prediction. Their prediction was pretty spot on. May not have been exact, but it's still within that range of what would have been considered normal. All right. Alternatively, you could have went to, sorry, not second. We could have just went to stats, went to test, went to number 2. This time we're dealing with just our statistics. Our mean for our hypothesis test was 25. The mean from our sample was 26.84. The standard deviation from our sample was 23.41. So that large standard deviation is why we ended up not failing the null hypothesis. We have 35. We have 35 as my sample size. And once again, I'm doing a two-tail test. We hit calculate. So like I said, there was a little bit of rounding on our part, so we're not going to get things exact. So this is 0.46. So in that case, that's probably a little bit of a typo on my end. When we got that p-value, so we got almost more, where was that? 0.64, which is what we had. So this still backs us up that we failed to reject the null hypothesis. We don't have evidence this analyst is wrong.